Hello and welcome to the presentation about the development of a concept for electrically conductive furniture panels. My name is Christoph Channen and I'm a junior scientist at Bern University of Applied Science. Before we get into the detail, let's go back to the origin of the idea. I will show you this on the example of interior lighting. You may know this problem yourself, a dark cabinet with not enough light where you cannot see what's inside of the furniture. Of course, the market came with their own solution of furniture having interior lighting already included. The classical interior lighting comes with the issue that wires and cables of the installation must be hidden somewhere within the furniture, and changes in the future are not so easily possible. Our idea was to go a bit further and use no electrical installation whatsoever and provide a flexible solution. Furthermore, interior lighting is only one part of the story. In the recent development, it seems clearly that daily objects must come with additional functions to fit to the new generation of customers. Such objects do then fit into the category of smart objects, fulfilling the need of the megatrend connectivity. An example of such furniture is shown here, although I have to say this is not what we had in mind at the start, but it shows what is possible and where the journey might go. The conductive particle board opens an opportunity to create more of these kind of furniture without using wires, but being highly flexible. So how does it work then? If you look at the furniture panel, you will have most likely a 3-layer particle board as a substrate, covered by a surface coating, which can be a veneer or an impregnated paper, and some edge bonding to cover the faces of the substrate. We tested different options with the modification of surface coating and edge coating, and also modification of the substrate itself. Although having very good results with the surface coating, the substrate was more promising due to a crucial detail of the structure. If you look at the 3-layer particle board, you have 2 layers separated by another. So we decided to only make the surface layers conductive. Thus we have an insulating core layer, and the surface layers act as the 2 phases of the electrical system. Furthermore, we also developed this prototype of a pin which you can press into a pre-drilled hole wherever you want, and it makes the best interface between the conductive panel and the LED. It can be basically referred to the light bulb that you turn into a socket, just that this time the entire panel is the socket. At the end it looks like this on this very first laboratory prototype. After the placing of the pin and connection of the power to the board, the light turns on. A patent application for the panel and the pin was meanwhile filled. We also created a small bench scale model, and you can see that the power is applied on the bottom part and the lights are placed in the middle part and the top part. The connection between the panels is a simple butt joint on a 45-degree angle. There are no issues whatsoever to create a connection from one board to the other without using any conductive connector. What we did at the end was mixing carbon fiber material into the matrix of the surface layer. We only tested carbon fibers this time as the budget of the project was very limited. However, we start a follow-up project beginning of August where we will look at different conductive materials. We did this with different concentrations to see how strong the effect of concentration is on the resulting resistance. The panels were produced in our laboratory in Biel using hot pressing. After the manufacturing of the panels, the resistance was measured using a multimeter. Here on this graph you can see the results of the very limited testing series of our panels. On the y-axis you can see the resistivity in ohm meters, where a lower value is better. The x-axis shows the concentration of carbon fibers in the surface layer material in weight %. At higher concentration it seems we have rather good resistivity values compared to the lower concentrations. However, there seems to be no big difference between the 10, 20 and 30% version. For the panels that I showed before, panels containing 10% of carbon fibers were used. If we look at these values in a bigger picture, we can see how these panels are positioned. You can see on this graph different materials ranging from very good conductors on the left to very bad conductors, the so-called insulators, on the right. The x-axis shows the resistivity, where lower values are better. You can also see the values of solid wood of different species and then compare it to the range of values measured from the conductive panels within this project. It is clearly visible here that the panels are far from copper, which sets the benchmark for a good conductor. But it is certainly an improvement compared to the values of the raw material of the panels, the solid wood. This is already the end of the presentation, and I hope you enjoyed it. Thank you very much for your attention. For questions, please contact me or Heiko Tömmen, or feel free to ask me in the following discussion.